All right, section 3 is inverse functions. And you learn this in Algebra 2. In fact, what we're about to do here comes straight off the Algebra 2 notes, so maybe it'll look familiar to you. Probably not. It should look really familiar to you.
Because I've been in 3 Algebra 2 classes.
That's right. All right, so I just want to refresh your memory on what inverse relations do, and then what inverse functions do before we get into the actual calculus that's in this section. So an inverse relation just switches the x and the y coordinates for every point that's in the relation. So if I give you a set of ordered pairs and I ask you to find the inverse, you just swap the x's and y's, and then that would be the inverse. Okay, straight out of Algebra 2. A great example of what this is actually doing is by just forming a triangle and then finding the inverse relation, so the inverse triangle. So we have these 3 vertices sitting here. A is -3, 2. Maybe we can remember how to plot points on a graph. B is 0, 1. I think that's there. And then C is 3, 4, like there. Okay. So that was A, that was B, and that was C. It does form a triangle. It's 3 points in space that are not all in a line. So I'm going to kind of try to draw in a nice triangle right here. Okay, now I want to graph the inverse relation. So what do I do? Switch all the coordinates. And the way that we designate a new set of coordinates is with the prime. So A prime will be 2, -3, B prime. Oh, and then C prime. Okay, so A prime is 2, -3, and then B prime is 1, 0, and then C prime is 4, 3. So there. Oh. All right, draw in my new triangle here, and what do you notice? Yeah, it's reflected across the line y equals x. So if I were to draw in a little y equals x line in here, then you would see that our original relation has been reflected in the line y equals x. That is what an inverse relation does. Basically, it reflects over the line y equals x. It's not good enough to live in Algebra 2, so we got to make it more complicated with inverse function notation. This is the formal notation for an inverse function. If we have a function f of x, then its inverse is written, what does that say? Yes. It says the inverse of f of x, or it says f inverse of x. How do I know that that's how I read that? Because it says right here. Yeah, do not read that as f to the -1st of x, because f to the -1st of x would imply that this is what you mean, and that's not the case. So that's something that you have to be very careful of. We talked about that in Algebra 2. So when you're dealing with an actual function, just like with the last page, all you have to do is switch the coordinates. So if you're given f of a equals b, to find f inverse, just switch the coordinates and get f inverse of b equals a. To find the inverse function, rewrite the function in terms of y, if necessary. Swap the x and the y's in the equation, and then solve for the new equation for y. And then if they ask you to graph it, go ahead and do that. So if I take my equation over here, f of x equals 2x minus 5, I'm going to turn that into y equals 2x minus 5, because my brain likes that a little bit better. And now I'm going to swap the x and the y, so this becomes x equals 2y minus 5. And now all I have to do is solve the equation for y. So I add 5 to both sides, and then I divide everything by 2, and I get 1/2 x plus 5/2 equals y. So just to double check to see if this is actually what happened here, we're going to graph this. 2x minus 5. I don't have minus 5 on there, but I can apply the slope. I'm at negative 5. I add 2, and I get to negative 3 over 1. I add 2, and I get to negative 1 over 1. And then I can just continue with my slope like that. So I have that line. And based on what we know about inverses, what can we say is going to be true about my graph when I graph it? It'll be reflected across the line y equals x. So I'll draw this one in red. We have 1/2 x plus 5 halves. That's 2.5, which is right there. And then 1/2, up 1, right 2. Up 1, right 2, up 1, right 2. Sure does look like it was reflected in the line y equals x. In fact, if I go ahead and put the line y equals x on there, there you go. So it does work, swapping the x and the y coordinates. Continuing with Algebra 2, the best way to check to see if two functions are inverses of each other, if you're given two functions, so this time they're actually giving you the two functions, is to check to see if the function compositions work out to be just x in the end. If they do, then they're inverses of each other. If they don't, then they're not. But the catch is you have to do both, f composed of g and g composed of f. Both have to work. It is possible that one will work and the other one won't. So you do have to check both. So are these two functions inverses of each other? Well, we need to remember how to do function composition. We've kind of been doing it all year, but we don't really usually say f composed of g and g composed of f. So let's do fog of x. What that means is f composed of g of x. So I'm sticking g of x in everywhere that I see x in f of x. So I start writing f of x, which is 3x plus 9. So I'm going to write 3 times. Good. Don't forget to finish off the function. So we distribute the 3 in, and we wind up with x minus 9 plus 9, which is just x. So it's looking good here. We got to do Goff as well. So g composed of f of x, which is the same as g composed of f of x. So what do I get? Okay, so 1/3 distributed in gives me which is, and there you go. So these two functions are inverses of each other. So let's go ahead and do these. What do we do? Oh, f composed of g of x. Distribute x so the answer is no. They're not inverses of each other automatically. Don't have to check the other one. All right, how about that second one? What do we do? Try Goff first, just for fun. Okay. 2x squared minus 1. Okay, so let's simplify some of the stuff in our head. The minus 1 plus 1 goes away. The 2's here go away. The square root of x squared is just x. We have to do both anyway. F composed of g of x, otherwise known as fog, is what? Okay, looks a little more complicated. The square root and the square go away, which leaves me with 2 times this stuff divided by 2, so the 2's go away, and I'm left with, which is, so are these inverses of each other? Yes. There are other ways to find out if a function has an inverse or not. In fact, a inverse for a function exists if and only if. So if and only if, you'll find out later on in math that you can go one way, you can go the other way. So if and only if means if this is true, then this is true, and if this is true, then this is true. Anyway, a function has an inverse if and only if the function is 1-to-1. And here's this vocab word again, monotonic. A function is 1-to-1 if it's monotonic. Monotonic means always either increasing or decreasing, but it never turns around. So in other words, a function has an inverse if and only if it passes the horizontal line test. Oh yeah, because a vertical line is up and down. And a horizontal line is left and right. So, if I put a horizontal line on this graph, is this one monotonic? Is it 1-to-1? No, because it does not pass the horizontal line test. The function goes through my horizontal line more than once. But if I move it down, then it still doesn't pass the horizontal line test. Because the whole point of the horizontal line test is anywhere along the function does it screw up. Does it do that? So let me undo that because I don't want that to happen. Okay, I actually want to grab this line though. Come on, grab the line. Line. No! Line. Grab the line. Line. Yeah, watch the video. I give up. How about on the other one? Can I draw a horizontal line there and pass it up and down the function and have it cross the function more than once at any given time? No. So this one has an inverse. This one is monotonic. It always is increasing. This one does not have an inverse. It is not always either increasing or always decreasing. Okay? So that's how you can tell from a graph whether or not there is an inverse. If the function's graph passes the horizontal line test, then it has an inverse. And then we can find it. So, is there a way for us to determine whether the function has an inverse without graphing? Yes. The answer is yes, of course. It must be either increasing or decreasing over the entire graph. And from what we know about calculus, that means that we can take the function and do what to it? We can take the derivative. And then we can find out if it's always increasing or always decreasing. And if we can do that, then we can say whether or not there's an inverse. So, these equations come off those two graphs that we just looked at. We already know that this one does not have an inverse and this one does have an inverse. So let's go ahead and take the derivatives of these two. They're easy to take. And then we'll look at the function itself and see how we can determine whether or not it's always increasing or decreasing or not quite the case. So f prime of x in this one is going to be what? So 3x squared minus 1. And f prime on this one is going to be okay. So take a look at this function right here. The way that it's written, the way that these signs work out, and the fact that we have an x squared sitting here. Is there any way that I can plug a number in here and wind up with a positive result? Yes. Is there any way I can take a number and plug it in here and wind up with a negative result? No. Because no matter what, when I square, I multiply by a positive, and then I add a positive, I'm going to wind up positive, which means that this function is always increasing. But in this case, is there any way I can wind up with a negative result? Yeah. And of course I can wind up with a positive result too. So that means that this one has places where it's increasing and decreasing. But this one has places where it's never, or sorry, this one only has places where it's increasing. This one's always increasing. So therefore, the vocab here would be, this is monotonic, and an inverse exists. The vocab on this one would be not monotonic. No inverse. So that's how you can use calculus. That's how you can use graphing. That's how you can use the functions themselves to find out whether there is an inverse or not. And the section will continue next time.